Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Magnetic Effect of Electric Current. Let's see today the working of an ammeter. An ammeter consists of a galvanometer and a shunt resistance. A resistance which is connected in parallel with it. You have current I entering point A, which will divide into Ig and Is. This is your shunt resistance. Will join back at point B and will move out. Right? So let us consider. Let G be the resistance. The resistance of the coil of the galvanometer right, which will give full scale deflection when current Ig passes through it, which gives full scale deflection. That means you will have maximum deflection when current Ig passes through it. Full scale deflection when current Ig passes through it. Right? Now, in that case, I can therefore say that it now in order that the galvanometer should be able to measure current I. At this point of time, the galvanometer is able to measure current only Ig. When current Ig passes through the coil of the galvanometer gives you full scale deflection. But I want the galvanometer to measure current I. In order to enable it to measure current I, it is necessary that to connect a shunt of small resistance across the galvanometer. In order that the galvanometer measures current I, it is necessary to connect a resistance, a shunt of small resistance across the galvanometer. So I have connected this shunt resistance which is across the galvanometer. Now, this shunt must be of such value that when current I flows through the circuit, Ig passes through the galvanometer and the remaining current should pass through the shunt resistance. Only then will it be able to measure current I. See, ideally the galvanometer can measure only current Ig, but I wanted to measure current I. So whatever it does, the maximum value of current that the galvanometer will be able to measure is only Ig. In that case, I have to make sure that I select the shunt resistor in such a way that only Ig current passes through the galvanometer and the remaining current should pass through the shunt resistance, right? So I can say that the shunt resistance must be of a value such that when current I flows through the circuit, current I flows through the circuit, only current Ig passes through the shunt Ig passes through the galvanometer. Only current Ig passes through the galvanometer, and the remaining current I minus Ig passes through the shunt. Right? So that means my shunt current now I know has to be I minus Ig. Total current minus the galvanometer maximum deflection current is the current that should pass through the shunt resistance. Now let us say that if Is is the shunt current, in that case I can say I is equal to Ig plus Is. Therefore I can say that Is is I minus Ig, but by Ohm's law we can say that if you look at the diagram, guys, if you look at the diagram, the galvanometer and the shunt are in parallel. Since the galvanometer and shunt are in parallel, the potential difference across the galvanometer and the shunt should be same. In a parallel circuit, the potential difference is constant. So if I apply Ohm's law also says that potential difference is nothing but the product of current and resistance. That means I can say by Ohm's law that galvanometer current into resistance of galvanometer should be equal to shunt current into shunt resistance. Right? I can substitute the value here. I can therefore say that Ig into G, Is can be written as I minus Ig into S. So in that case I can say that Ig is equal to Is minus Ig. Ig into G is Is into minus Ig into S. Take Ig on the other side, so I'll get G plus S into Ig is I into S, in which case I can therefore say that the galvanometer current is I into S upon G plus S. Right? This tells you exactly what is the amount of current that will be flowing through the galvanometer. If I connect a shunt across the galvanometer, then this is the exact amount of current. This is the total fraction of the current that will be flowing through the galvanometer. Right? I can also say that we have said that Ig into G is I minus Ig into S. Right? In which case I can find out the value of shunt resistance also. S will be nothing but Ig into G upon I minus Ig. This expression will tell me the proper value of shunt that should be connected across the galvanometer, so that the galvanometer shows maximum deflection when current I flows through it. Fine, do we get this in clear? Let's also try to find out the value of shunt current. I can say also Is into S is nothing but Ig into G. So in that case I can say that Is into S, Ig can be written as I minus Is into G. Therefore I can say that Is into S is equal to I into G minus Is into G. Take this on the other side, so I can get Is S plus G is I into G. Therefore the shunt current is going to be I into G upon S plus G. That will give me the exact value of shunt current that will be flowing through the circuit. Fine. So with the help of this derivation, we exactly know the value of shunt resistance, We know the galvanometer current that will give you maximum deflection, and we know the shunt resistance as well as the shunt current. Right? So this was about ammeter. Now let us move to voltmeter. Like an ammeter is a device that is used to measure current. A voltmeter is a device that is used to measure the potential difference across the ends of the conductor carrying current. A voltmeter is an instrument used for measuring potential difference across the ends of the conductor carrying current. Right? That is what is the voltmeter. Now, we know that a voltmeter is going to be connected in parallel. If I want to measure a potential difference, that means the voltmeter has to be connected in parallel. Now, if it is going to be connected in parallel, what are the problems that you will face? The introduction of voltmeter in the circuit, the introduction of voltmeter in the circuit will lower. I'm connecting a resistance across it. Now when you connect resistance in parallel, the net effective resistance of the circuit gets lowered, right? This may lower the value of potential difference, lower the value of potential difference between 2 points, and the lower value will be measured by the galvanometer. If I introduce the galvanometer in the circuit, some amount of potential difference is going to be will flow through the galvanometer, and this is going to lower the total amount of potential difference that is going to flow through the circuit. Secondly, even if a small potential difference is applied to a galvanometer, it will give full scale deflection, because the coil of the galvanometer has a limited value of resistance, right? Hence, some modification is necessary so that the galvanometer can measure large potential difference. Even a small current is giving you full scale, small potential difference is giving you a full scale deflection, right? Next, a small potential difference gives full scale deflection on the galvanometer. Right? Hence, some modifications are necessary. Some modifications are necessary in order to measure large potential difference, right? Third, as the potential difference is applied across the terminals of the galvanometer, a large current will pass through the galvanometer coil, which will cause the damage of the coil. You also have to protect the coil of the galvanometer. If I'm going to connect this in the circuit with very high potential difference, large amount of current will flow through the coil that could cause the coil to get burned, right? So, large potential difference applied across the terminals would uh, would lead to large current flowing through the coil of galvanometer which will cause damage to the coil. Right? These are the three problems that you face when you try to use a galvanometer as a voltmeter. Right? Now, in order to overcome these three problems, the simple method that has been devised is to connect a resistance in series with the coil. Right? Thus, I can say that a galvanometer can be converted to a voltmeter by connecting a resistance in series. With the coil. Right? Now let's see how does this enable us to convert a galvanometer into a voltmeter. Let's draw the figure first. This is your galvanometer. I'm connecting a resistance in series with the galvanometer, right? And this is your R, and these are the ends across which the potential difference V is going to be applied, right? So let us consider a galvanometer of resistance G, giving full scale deflection when a current of Ig flows through it, and a current of Ig flows through it. Yeah, you want to ask me something?
The resistance should be R as the galvanometer resistance.
I'm considering the galvanometer resistance to be G. The galvanometer resistance is G, and the series resistance I'm going to consider it as R. Fine, do we get this thing here? Now, let us assume that V is the potential difference let V be the potential difference measured then a high resistance R is connected in series with the galvanometer. To measure that high potential difference, I'm connecting a resistance R in series with the galvanometer. Right? Now, the series resistance that should be connected should be such that, now why do I need the series resistance? What is the purpose of this resistance? This series resistance must be such that when potential difference V is applied across the series combination R and across the series combination, the current Ig should flow through the galvanometer and give full scale deflection. Current Ig should flow through the galvanometer. Fine, do we get this thing there? Now, since G and R are in series, I can therefore say that the total potential difference applied is going to be used by the potential difference of the galvanometer and the potential difference of the series resistance, and by Ohm's law I can say this is going to be Ig into G plus Ig into R. Why Ig into R? Because the galvanometer and the resistance are in series, so same current will flow through them, right? In which case I can say that the potential difference V is Ig into G plus R, right? In which case I can say V upon Ig is G plus R. Therefore the value of the series resistance is V upon Ig minus G. That will tell me what is the exact value of series resistance that I should connect, so that current Ig gives a full scale deflection, right? So now we know how to convert a galvanometer into voltmeter. Now let us try to find out the sensitivity and the accuracy of a moving coil galvanometer. Now first of all, for that we need to know what do we understand by the word sensitivity. Now if d theta is a change in the deflection caused by a small current di, then this ratio of change in deflection to change in current is called as sensitivity. How much will be the change in deflection if I change the current by a small amount? This particular ratio is defined as sensitivity. Fine, do we get this thing clear? So, sensitivity. How do I define sensitivity? If d theta is the change in deflection caused by a small change in current di, then the ratio d theta upon di is called sensitivity of the galvanometer. Fine, do we get this in clear? That means I can say that, let's try to find out the sensitivity of a galvanometer. Now we have derived that in the case of a moving coil galvanometer, I can say that current, guys, if you look at your previous derivation, your last lecture's derivation, current we had defined as K upon NBA into theta. This is how you had found out the value of current. So in that case, I can say that theta is going to be nothing but NBA upon K into I. That will be the deflection. Now differentiate both sides with respect to I. Differentiate with respect to I. So I'll get d by di of theta is d by di of NBA upon K into I. this will give me di by d theta, sorry, d theta by di. Whatever is constant comes outside the derivative, so the nda upon k comes out as it is. D by di of I is 1. Thus, the current sensitivity is equal to nba upon k, right? Which shows that the current sensitivity depends upon the number of turns of the coil, depends upon the area of the coil, depends upon the magnetic induction, and depends upon the torque per unit twist of the suspension fiber. So it is directly proportional to the number of turns of the coil, is directly proportional to the area of each coil, is directly proportional to the magnetic induction, and is inversely proportional to the torque per unit twist of the suspension fiber. Fine. So do we understand how do we get sensitivity? Next, that means if you are asked a question that how will you increase the sensitivity of a galvanometer, you know the factors that will cause the increase and the decrease in the sensitivity of the galvanometer. Next, let's move on to accuracy. Now, for a moving coil galvanometer, we have already derived the relationship. For a moving coil galvanometer, we know that I is equal to K NDA into theta, right? Now, N, D, A and K are constants for a given galvanometer. The accuracy of the measured current therefore depends upon the accurate measurement of the deflection theta. How accurate your moving coil galvanometer is depends upon how much is your deflection for the given current. Let us assume, let's write this down. Here K, N, B and A are constants. Therefore, the accuracy of a moving coil galvanometer in measurement of current depends upon the accurate measurement of deflection theta. Right? So let us assume that d theta is the error in the measurement of deflection theta. Let d theta be the error in the measurement of theta. If d theta is the error in the measurement of theta and di is the corresponding error in the measurement of current I, di is the corresponding error in the measurement of current I, then how do I define accuracy? Accuracy will be nothing but the accuracy of a moving coil galvanometer is expressed in terms of relative error. That means it is expressed in terms of the error in current to the total current. Then accuracy is expressed in terms of relative error di upon I. So accuracy of a moving coil galvanometer is measured in terms of relative error di upon I in the measurement of current I. Right? Now, we already have said that I is equal to K upon NBA into theta. Right? Now, if I differentiate with respect to theta, I will get di by d theta is nothing but K upon NBA. D by d theta of theta is 1. So in that case, I can therefore say that di cross multiply is K upon NBA into d theta. Right? Now, divide this by I. If I divide this by I can say that di upon I is nothing but di. We just found out the value of di to be K upon NBA into d theta upon I. I is nothing but K upon NBA into theta. Therefore, I can say that di upon I is nothing but d theta upon theta. Right? That means for greater accuracy of this shows that as greater accuracy of di upon I is smaller. If I want a greater accuracy, that means the value of error should be as small as possible. Right? That means d theta upon theta should be as small as possible. That's how you find out the accuracy of a moving coil galvanometer. Next, let's see the construction of a tangent galvanometer. Construction of a tangent galvanometer. Right? Draw the diagram down, guys. Let's see the construction of a tangent galvanometer, people. Now, a tangent galvanometer, as you can see from the diagram, consists of a circular coil of insulated wire, right, which is wound on a non-magnetic frame. So, this is your non-magnetic frame on which you have this coil that is wound. Ordinarily, two or more coils are wound on the same frame so that we can use different number of turns. Now, in the given figure, you have a tangent galvanometer with a circular frame which is fixed vertically on a heavy horizontal base. This is your horizontal base on which it is fixed, which is provided with your leveling screws. Okay, a short magnetic needle is placed at the center of the coil and can rotate in the horizontal plane. A long thin aluminium pointer is pivoted at right angles to the needle and shows the deflection, which is divided into 4 quadrants of 90 degrees each. A plane mirror is kept below the pointer, which helps to measure the deflection without parallax. So you have a mirror that will give you that reflection, right? Right? So that's your construction of a tangent galvanometer. You have a coil that is kept on a heavy base. The heavy base is provided with leveling screws, and you have a needle that is kept in the center of the coil. You have a mirror that enables you to read the deflection of the needle. Can you just write this much down, people, please? Construction of a tangent galvanometer. It consists of a circular coil of insulated wire which is wound on a non-magnetic frame the tangent galvanometer with the circular frame with the circular frame fixed vertically on a heavy horizontal base. Fixed vertically on a heavy horizontal base provided with leveling screws. The frame can be rotated about vertical axis. So that's the first part. A short magnetic needle is pivoted at the center of the circular coil. A short magnetic needle is pivoted at the center of the circular coil and can be rotated in a horizontal plane. Be rotated in horizontal plane. A long thin aluminium pointer is pivoted at right angles to the needle. A long thin aluminium pointer is pivoted at right angles to the needle and shows the deflection of the needle on a horizontal circular scale. Shows the deflection of the needle on a horizontal circular plane. Horizontal circular scale. A plane mirror is kept below the pointer. Plane mirror is kept below the pointer and helps to measure the deflection of the pointer. Measure the deflection of the pointer. Right? So that is the construction of your tangent galvanometer. Right? We will stop this here for the day. Thank you very much.